So the large quadricep muscle in the upper leg terminates at its lower end in a tendon attached to the upper end of the tibia in figure A. The forces on the lower leg when the leg is extended are modeled as in figure B, where T is the force of tension in the tendon, W is the force of gravity acting on the lower leg, and F is the force of gravity acting on the foot. Find the tension when the tendon is at an angle of 25 degrees with the tibia. We are going to assume that W, or the weight of the leg, is equal to 33 newtons. The weight of the foot is the force of gravity due to the weight of the leg. The force of gravity due to the foot is equal to 12.9 newtons, and theta is 40 degrees. Remember that this is theta, so I'm going to call this theta 1 and this theta 2. So this is theta 2 is 40 degrees, theta 1 is 25 degrees. Assume that the tendon attaches to the lower leg at a point 1/5 of the way down the leg. So the length to the tendon is going to be equal to the length of the leg divided by 5, right? Because this is just 1/5 times the total length of my leg. The weight of your leg is 1/2 the way down the leg. So length to the weight of my leg is going to be L over 2, right? Because that's just 1/2 times L. And then my foot is obviously at the end of my leg, right? So L of your foot is just going to be equal to L. And then we are going to want to find tension. So we want tension. And what am I going to use? So in order to figure out what I'm going to use, the first thing I'm going to do is draw this force diagram here. So I will change this to black. So I have the weight of, I'm going to zoom this in for everybody. I have the weight going down, so I will have the X component going this direction, the Y component going that direction. Because this line and this line are parallel to each other, I can assume that this theta is the same as that theta. Also, I have the foot, but I will have the X direction of the foot, I will have the Y direction of the foot, and I can assume that this is the same theta. The other thing I need to consider is this force due to the tendon or tension of the tendon, and I will have the Y component and I will have the X component here. So I drew my force diagram. Great job. Now I'm going to follow my own instructions. I'm going to write out the torque for each one of these forces. So I'll do this over to the side here. So I have the torque due to tension. This is going to be the length due to tension, like how far away this force is from my pivot point. Obviously my pivot point is my knee. So I need to know how far away that is. That's going to be L times T. I will have my force of tension, and then I need to figure out whether I'm going to use sine or cosine here. So what I'm using is I'm using the torque is equal to RF sine theta, or torque is equal to RF cosine theta. Which one of these depends on the location of the angle in your triangle. So for the torque due to my tendon, I'm going to want to consider what is, in order to get the perpendicular component of this force of tension, right? So in order to get my y component here, I need to figure out if this is going to be a sine or a cosine. So because this is opposite, right? All I did was just translate that over. Because this is opposite of my angle, this is going to be sine of theta 1. And I'm going to go ahead and figure out the directionality of this. So if I do R cross with F, it's going to come out of the page. So this is going to be a positive torque. Now, what about the torque due to the weight of my leg? Well, this is going to be the distance to the weight of my leg, the force of the weight of my leg, and then I need to figure out if this is sine or cosine. So I'm going to want this component. So this is opposite. So this will also be sine, but this will be sine of theta 2. And the directionality that this is going to go is going to be negative because the torque is going to be going into the page. And I will do the same thing with the foot. This will also be sine of theta 2, and this will also be negative. So in this situation, all of these are going to be sine. So I wrote out the individual torques, and I determined the direction of each of my torques. Now I need to write out the distances. I did that. I figured out how far away each one of these is acting. So now I just need to create a summation of torque equation. So for that, I'm going to use that all of my torques are in equilibrium. So for that, I have the summation of torque is going to be equal to 0. Now I need to just incorporate all my torques here. So I will have the torque due to the tension of the tendon plus the torque of the weight of my foot plus the torque, no, sorry, that was the weight of my leg, plus the torque due to the weight of my foot. I'm now going to replace all of these with the equations I have above, including and incorporating my directionality here. So also this will be equal to 0. So for the torque due to the tension, it'll be LT FT sine theta. LT FT sine theta 1. And that has a positive directionality. I have a negative directionality for the weight of my leg. And I have a negative directionality for the weight of my foot. And this has to be equal to 0 because it's in equilibrium. The next thing that I want to do is I'm actually going to replace all of these little L's, the distances, with the uppercase L that I have, where L represents the length of my leg. Well, I guess honestly just the length of my tibia, but so this will be LT is L over 5 FT sine theta 1 minus L over 2 FW sine theta 2 minus L F sine theta 2, and this will be equal to 0. And notice that I have L in all of these terms in my equation, so I can actually just cancel, I can actually just cancel out these L's. So my new equation would be 1/5 ft sine theta 1 minus 1/2 fw sine theta 2 minus the force of my foot sine theta 2, and it will be equal to 0. So in this problem, they asked us to solve for the tension force. So I just need to rearrange this equation to get the force of tension by itself. So the first thing I'm going to do is I'm going to add 1/2 fw sine theta 2 and the force of the foot sine theta to both sides of my equation so that I can move this over. That will give me the new equation of 1/5 ft sine of theta 1 is equal to 1/2 the force of the weight of my foot sine theta 2 plus the force of the weight of my foot sine of theta. The next thing I need to do is I need to divide both sides by sine of theta. So I get 1/5 ft is equal to 1/2 fw sine theta 2 plus the weight of my foot sine theta 2 divided by sine theta 1. My sine thetas don't cancel out because these thetas are different. And then I'm going to multiply both sides times 5 to get rid of that fraction. So this will be 5/2 fw sine theta 2 plus 5 the force of my foot sine theta 2 divided by sine of theta 1. At this point in time, you could input numbers, but I like to minimize the errors that I can have with my calculator, so I'm going to simplify this a little bit more. I am going to drop this 2 down. So when I do that, I will end up with 5 fw sine theta 2 plus 10 ff sine theta 2 divided by, I dropped my 2 down, 2 sine of theta 1. So now I can just plug in all my numbers. So this is 5 times, what was the weight of my leg? Is 33. Sine of theta 2 was 40 degrees, plus 10 times the weight of my foot was 12.9. Sine of 40 degrees. I could have simplified this more and pulled my sine of 40 degrees out. I should have done that. Times 2 sine of 25 degrees. And this will give me degree times sine of 40. 106.1 plus 10 times 12.9 times sine of 40 is like 83 roughly, divided by 2 times sine of 25. This would be 0.85-ish. And I get 106.1 plus 83 divided by 0.85 is 223-ish, 223 newtons. My answer should have been 224, so this is close enough for me to consider it to be correct, but with some amount of rounding errors that I incorporated there. I would probably get closer to the correct answer if I had pulled my sine of 40 out and done this calculation, but for me, this is close enough to feel like it is correct and that my approach was correct.